Ilalaban kahit kanino, oo, simple lang ako at malabo mong magtipuhan. Kaya okay nang kahit sa FB mo lang mapusuan. Kasi di na mapigilan ng sariling mapaibig sa iyo. Ano ba to? Gusto ka laging...
Okay, now let's move on to our next topic. So last time we have learned about SP3 hybridization, about for methane and ethane. So we have learned that SP3 hybrids were formed in methane for CH bonds, and for ethane there are CH bonds, and at the same time there are also CC bond, which are also SP3 hybridized. Okay, so it's not all the time that all of the compounds or molecules are actually SP3 hybridized. So there could be an SP2 hybridization, and some of them could have been SP hybridized. Okay, so let's talk about it now. So bonds in methane are called single bonds. So we have learned earlier that those SP3 bonds in methane are actually single bonds because they have only one bond. Okay, so the bond there is actually called a single bond. Okay, that means they shared only one electron pair. Diba? I told you that each of those bonds contain two electrons. That means they are actually called an electron pair. Okay, so if they share only one electron pair, then they are called a single bond. So as we have seen the bonds or the line bond structure for methane and ethane. However, carbons can also form double bonds. That means it can share its two electron pairs. So it can share two electron pairs with other atoms, or it can share three electron pairs with other atoms. So it can form double bonds or triple bonds. Okay? So example of this is actually ethylene and acetylene or acetylene. So what is the chemical structure for ethylene? So this is the chemical structure for ethylene, while acetylene is this one. So as you can see that carbon can actually double bond to another carbon, okay, for ethylene. And for acetylene, you have carbon is triple bonded with another carbon. Okay, so for ethylene, actually the hybridization for carbon for both carbon here is actually SP2, while for acetylene it is actually SP hybridized. So when you say SP2 hybridization, that means the 2s is actually mixed only with the two 2p orbitals, which is the px and the py. Okay, so the s orbital of your carbon is actually mixed with your px and the py, leaving behind your pz degenerate orbital, which is actually unhybridized. So we have one unhybridized orbital, while the s, the px, and the py are actually hybridized. So that means we have one s and we have two p, so that becomes an sp2 hybridization. While for sp hybridization, okay, the s orbital for carbon is actually mixed with the px of the px orbital, okay, or px degenerate orbital. So the s and the px are mixed together to form an sp hybrids, leaving behind your py and pz to remain unchanged, and at the same time they are not hybridized or unhybridized. Okay, so what happened to those unhybridized orbitals? So we will learn that when we later we learn that later. Okay, so let's first to differentiate what is an sp3 and sp2 and sp, so how they differ to each other. Okay, for sp3 hybridization, okay, for sp3, the 2s orbital of the carbon combines with all the three 2p orbitals. We have three degenerates orbitals for P, you have Px, Py, Py, and also the Pz. Okay, correct? So you have three degenerate orbitals. So that means all of the 2s orbital of carbon can be combined with all of these three 2p orbitals of the carbon to form four equivalent high sp3 hybrids. Okay, that's why your carbon in methane can combine into four hydrogens because you have four equivalent sp3 hybrids. Okay, how about in sp2? Okay, the 2s orbital only combines with the two 2p orbitals to form three equivalent sp2 hybrids. So your 2s orbital can only be combined with px and py for sp2. Okay, leaving behind your pz orbital. So your pz now becomes unhybridized. Okay, while for sp, the 2s orbital combined with one 2p orbital to form two sp hybrids. That means that your s or your 2s orbital only combines with your px, leaving behind your py and your pz to be unhybridized. Okay? So all orbitals are hybridized in sp3. That is correct. So all the orbitals, the s and the three 2p's are all hybridized. While for sp2, we have one unhybridized p orbital that is actually pz. While for sp, we have two unhybridized 2p orbitals that is py and pz, and those unhybridized orbitals remain unchanged. Okay, both sp3, sp2, and sp are unsymmetrical about the nucleus because the s can be added with a p to have a so that your p lobes, the other side of the p lobes would have a bigger size lobes. Remember yet that your dumbbell shape for P. Okay, so when we add our S orbital that is spherical plus a dumbbell, so the equivalent now would have been longer lobes, bigger lobes for and a smaller lobe. Okay, so that means this is now unsymmetrical to the nucleus, and since it's unsymmetrical to the nucleus, then all of the bonds should be strongly oriented in a specific direction. Okay, so they all have specific direction. On what direction are they going to have their bonds, and also on what angle, and what is the position of the atoms. Okay, so that means that for sp3, that is band angle is more likely 109.5 degrees. That is for methane, and we also did the band angle for ethane and the propane, which is actually greater than 109.5 degrees. What was the explanation for that? It's because of the sigma bond or the sp3 bonds that is coming from the carbon to carbon bonds, or the single bond in carbon to carbon, which actually allocates a greater space because of electrons. Okay, that is why there is what we call an electron pair repulsion. But because of those electron pair repulsion, the band angle for ethane and propane are actually greater than 109.5 degrees. Okay, for sp2, we will see it on our diagram that is actually 120 degrees. And for sp, that is equivalent to 180 degrees. Okay, this is now the diagram that shows an sp2 and an sp hybridized. So remember, okay, that in your sp2, you have one p orbital that is actually anhybridized. So you notice this lobe here, the pink and the blue one, that is your p orbital that is actually unhybridized. So you have one p orbital unhybridized, and you have your hybridized sp2 equivalent of three equivalent sp2 hybridized. Okay, three equivalent sp2 hybridized. Okay, So that means that they arrange themselves so that there will be no repulsion on the side. The other one, there will be no reduced repulsion because of electrons. So when 360 divided by 3 equal sides, that becomes 120 degrees. So the band angle here and there is 120 degrees. Okay? So that is an SP2 hybridized. For SP hybridized, so you can see that there are actually two, that is one, diba? This is one P and the other one is at the back, that is actually PZ. Okay, so there are two unhybridized P orbitals, leaving your PX to be mixed with your S orbital, then you can form an SP hybridized. So the green one is the hybridized orbital, while those that are actually not in the green color are unhybridized. Okay, so that means that your 180, your SP hybridized will actually have its structure to have a band angle of 180 degrees to reduce repulsion of electrons. That is actually also according to the DSTPR. Okay? Okay, let's first discuss the properties for SP2 hybrids. Okay, so example of SP2 is what we have learned earlier is ethylene. Okay, so ethylene contains a C double bond C, okay, and a C single bonded to hydrogen. Okay, so the sp2 hybridized carbons of ethylene will form a strong bond by sp2 head-on overlap. Okay, so there is an sp2 head-on overlap, or what we call the sigma bond. So the head-on overlap of this is a sigma bond. So that is what we call a sigma bond. Okay, so the single bond that we notice in the ethane and methane is actually the sigma bond. So that is what we call the head-on overlap. Okay, so the remaining bond, so that's why there is a double bond here. The second bond there is actually, that is the unhybridized p orbital, which actually interacts to the p unhybridized p orbital of the another carbon, which they overlap in a sideways position. Okay, so the overlapping of the sideways position, so the interaction is sideways overlap, forming now your pi bond. Okay, so that means that your double bond, your C double bond to C carbon, contains a head-on overlap, which is what we call the sigma bond, and the sideways overlap, which is the pi bond. Okay, so what do you call the sigma bond? That is actually an sp2 head-on, and your pi bond is the unhybridized p orbital for both of this carbon. Okay, so both the sigma and the pi bond will form the double bond in C double bond C carbon. Okay, so this is now the graphical or the illustration for that. Okay, so you have your p and hybridized orbital, and this is for one carbon and this is for the second carbon. Okay, so the three lobes here in green are the hybridized, while the unhybridized is the color pink and the yellow. I mean the pink and the blue. And this is for another carbon. Okay, so this interaction here is what we call an sp2 cc sigma bond. Okay, so this will interact with each other to form an sp2 cc sigma bond, and the p orbital of the first carbon and the unhybridized p orbital of the second carbon will also interact sideways. Okay, so it should be that a bond will form should be symmetrical to each other in order for a bond to form. Okay, so this can interact with this because they are actually symmetrical. And this p orbital here and the other p orbital there can interact with each other because they are actually symmetrical. So your P here, this one, and that P, and this P or this lobe here will not interact with your P because they are unsymmetrical. Okay, so take note of that. Bonds will only form if the opposing atom will have a symmetrical lobe or a symmetrical orbital. Okay, so that an overlapping of orbitals will happen. Okay, so this is now when this interact with this, it will overlap to form your sigma bond, and your p orbital will also overlap sideways to form your pi bond. So a double bond is composed of one pi bond and one sigma bond. Okay, so example of that is actually our ethylene. Okay, so ethylene has a distance of 134 picometer, okay, and a band angle of around for HCC band angle, that is 121 or around 120 degrees Celsius, not Celsius, degrees. Okay, so that's it for SP2. So it's actually a trigonal planar. So it's a plane. So it's not the trihedral, but it's actually a trigonal planar molecule. Now let's move on for the SP hybrids. So in SP hybrids, so the SP hybridized carbons will form a strong bond by SP-SP head-on overlap. So there is a sigma bond. Okay, there is a sigma bond there in a triple bond, and the two unhybridized p orbital will interact by sideways overlap. So the remaining two bonds there are actually pi bonds. It's not sigma bond anymore. The sigma bond is only one head-on overlap, and the two bonds are actually pi bonds, which are sideways overlap. Okay? So both the sigma SP-SP for carbon and carbon, and the two pi bonds for PY, and PZ. So the PY of this will interact with the PY of this, and the PZ of this carbon will interact with the PZ of that carbon to form the triple bond. Okay? So one sigma bond, and two pi bonds will form a triple bond. So this is now the illustration for that. So we have here the two hybridized orbital, and we have your two unhybridized p orbital. Okay, so this one here will form an SP interaction for both your carbon, which can form a sigma bond, and the remaining p orbitals, like this pink color here and the blue one, will now form your pi bond, which are actually sideways overlap. So you have one sigma bond and two pi bonds. Okay, you can form a triple bond. For C, triple bond C, the band angle is 180 degrees, and the bond length for C, double bond C, is 120 picometer. That is actually lower than your ethylene. So this is acetylene. So lower than your C, double bond C, and also lower than the single bond for CC for ethene. Okay, so we will also differentiate the bonds there for ethane, ethylene, and acetylene, and let's talk about which is actually a more stable bond and the strongest bond. Okay. So here's the different here is the differentiation or the comparison between your ethane, ethylene, and acetylene in terms of hybridization, band length, band strength, and band angle. So we can for ethane, hybridization is sp3. For ethylene, that is sp2. You know already that because this is a double bond. For acetylene, that is sp because this is a triple bond. Okay. For band length, that is for ethane is 154 pm or picometer. That is actually we're talking about CC bond here, not CH bond. Okay. For ethylene, that is the C double bond C is 134 picometer. For acetylene, that is 120 picometer for C triple bond C. So for bond length, you have observed that the lowest bond length would have for acetylene, which is actually 120 picometer. While for bond strength, in terms of kilojoules per mole, we have here for ethane 377, ethylene 728, acetylene is 965. That means the bond strength, the one that has the biggest bond strength is actually the triple bond. So that means your acetylene is actually the most stable among the ethylene and ethane. Okay, since it has the greatest amount of bond strength. Okay, so you can't really break the bonds between your C triple bond with C in an easy manner or in normal condition, because it needs a lot of this energy to break that particular bond. So that means it's very stable bond compared to your double bond and your single bond. And here also is the band angle, which is 111.2 for ethane, for ethylene 120 degrees, and for acetylene that is 180 degrees, which is linear. For acetylene, ethylene is trigonal planar, and for ethane is more likely tetrahedral, just like your methane. Okay, so we have here a sample problem for what we have learned earlier about SP3, SP2, and SP hybridization. So, sample number 1, formaldehyde, which is a formula of CH2O, contains a carbon-oxygen double bond. Draw the electron dots and line band structures of formaldehyde and indicate the hybridization of the carbon atom. So, how do we do that? So, given is that your CH2O is the formula for formaldehyde, and it contains a carbon-oxygen double bond. Okay, so carbon would be our central atom. Okay, draw the electron dot and line band structure. So for electron dot, we know that carbon has a how many valence electron? 4 valence electrons. So 1, 2, 3, and 4. Okay. Since your carbon is actually double bonded to your oxygen, so when we say double bond, how many electron pair is being shared or are being shared by your carbon? They are actually 2 electron pairs, okay? So that means 2 electrons here, and the other 2 electrons would be coming from your oxygen, okay? And the total of 4 electrons, okay? So I will just write it closer to the carbon, okay? So we have 2 electrons coming from your oxygen atom, okay? So since 2 electrons are being shared to form a double bond with your carbon, what is the valence electron for oxygen? 6 valence electron. So how many electrons are left now? They are actually 2 electron pairs, or a total of 4 electrons. So 1, 2, and 3, and 4. Okay? So they are already 2 electron pairs left, or what we call the lone pair. So there are 2 lone pairs left for oxygen. Wait. So as you can see that there are actually 5 electrons from your carbon. So it doesn't coincide with our 4 electrons. So we will erase the other one. So we will erase that because we only have 4 valence electron for carbon. Am I right? Okay, so we will erase that electron. So how many? So the remaining 2 electrons now would be coming from your hydrogen, which is because your hydrogen is actually has 1 valence electron. So it will share to your carbon. Okay, so the remaining 2 electrons of the carbon would be shared by your hydrogen because your hydrogen has one valence electron. So this is now the electron dot structure for formaldehyde. Then if you're going to draw the line band structures, then you can also draw it. Okay? So your carbon is double bonded with your oxygen. And don't forget the lone pairs for oxygen. And you have one bond for your hydrogen and the other bond is for another hydrogen. Okay, so this is now the line bond structure for your formaldehyde. Okay, next. Okay, don't forget that your carbon can only be bonded into 4 bonds. And don't forget that the valence electron for carbon is 4 valence electron. Okay, number 2. Draw the electron dot and line band structure of hydrogen cyanide, HCl, and determine the hybridization of the carbon atom. We actually didn't determine the hybridization for the CH2O. Okay, so I will write first. Okay, we'll go back to number 1. I forgot it. Okay, double bond with your oxygen. Sorry for the drawing. Okay, going back to formaldehyde. Okay. So since your carbon is actually double bonded with your oxygen, then your carbon here is an SP2 hybridized. Okay, that's correct. So that is an SP2 hybridized. So automatically, if it is a double bond carbon, then the carbon is actually an SP2 hybridized. Forgot the hybridization. Okay, it's okay. So number 2. So you can pause this video so that you will have a time for you to find the structure, the electron dot structure and the line band structure for hydrogen cyanide. So you can pause the video. Okay, now for hydrogen cyanide. Okay, so carbon is a central atom. Okay, electron dot. So how many electrons are there in carbon? So there are actually 4 electrons. Okay, 4 electrons per carbon. Okay, for hydrogen, what is the electron dot formula for hydrogen? You have only 1 electron. And for nitrogen, there are actually 5 electrons. Okay, so 1, 2, 3, 4, 5. Okay, so how do you do this? Okay, so since you notice that your nitrogen has actually 3 electrons that are not paired. So that means that these 3 electrons here that are not paired in your carbon can be paired with your nitrogen. Okay? And the remaining 1 electron can be paired with your hydrogen so that both your carbon and nitrogen will obey the electron rule, the 8 electron rule or the octet rule. So how do you do that? Okay, so carbon, 3 electrons. Okay, and you have your 3 electrons coming from your nitrogen. Okay, then you write your nitrogen and the remaining electron pair, which is actually a lone pair. Then the other side would be from the hydrogen. Okay, so that's it. So you notice that both your carbon and your nitrogen follows the electron rule or the octet rule. You have 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4. 4 pairs, that is 8 electrons. 1, 2, 3, 4, that is 8 electrons. Okay? So how do we write its line bond structure? So this is one for CH bond, and you notice that it is actually a triple bond. Okay, so 1, 2, 3. And don't forget your lone pair for hydrogen. So this is now the line band structure for hydrogen cyanide. So the hybridization for carbon, since it is a carbon triple bond with N, so therefore the hybridization is SP. And we're done.